live stream. Hold on. Looks good. Hello, Gaetano. Are you ready?
Yes, I'm ready.
Hello, good morning, good afternoon, and good evening. Welcome you again to this World River and Delta Source to Sink webinar series. And this is Paul Liu from NC State University. And this talk series is co-sponsored by ISF, NC State, Louisiana State University, State Key Lab of Estuary and Coastal Research, East China NOMO, and Utrecht University in Netherlands. So today we are very happy to invite Dr. Gaetano Porcile from France, University of Caen, Normandy, come here talk about the tropical cyclones impact generated turbidity current offshore in Philippines, small river deltas. So before I introduce Gaetano, so I always like to mention all our previous talks, including this one, have already been and will be archived on our YouTube channel. So you can access all the talks for your research and education purpose as soon as you give a credit to the speakers. So at the same time, we also maintain a Twitter account, Source to Sink. So all the future talks, some event will be posted there. So you are welcome to follow us. So next week, the same time on Wednesday, Tim Dalpena from Texas A&M at Galveston will come here also talk about the dramatic natural feedback for the human impact on the estuary in South Korea and Texas. So welcome you, mark your calendar, come here back again. Gaetano, as I mentioned now, is a postdoc fellow at the University of Caen, Normandy. So it's the Morphodynamic Continental Research Center, I guess. So, so as you can see here, originally he from Italy, graduate University of Genova, and is Department of Civil, Chemical, and Environmental Engineering. So his research mainly focused on environmental process related to the water sediment mix and the interaction in, particularly that's sediment transport, sediment dynamic in a marine environment. And most recently, he studied in South China Sea, in offshore of the Philippines, the storm impact, sediment transport, and the canyon related sediment dispersal to the deep sea. So Gaetano, now I welcome you to our talk series. Thank you very much.
I'm sharing the screen. Can you see the presentation?
Yes, you can, yeah.
Okay. Hi, Paul. Hi, everyone. So first of all, thank you, Paul, for hosting this great webinar series. I learned a lot from the different seminars you collected. And thank you for inviting me. I'm really happy to can give my contribution. And especially talking about my research activity in 2020 that I couldn't present in a proper way during the pandemic crisis. So the project I will talk about was carried out at the University of Genoa in collaboration with Shell. I was working under the supervision of Michele Bolapitaluga from Genoa University and Alessandro Frascati, Octavio Sequeiros, and Carlos Pirmez from Shell. And our main research question was how do tropical cyclones can generate turbidity currents offshore small river deltas? And today I will try to answer these difficult questions with insights from two study cases in Mindoro Island in the Philippines. In the background, you don't see Mindoro Island. This is New Caledonia after the passage of tropical cyclone Niren in 2021. But since the physical settings are pretty much the same, I'm expecting an extending island forced by a tropical cyclone. I'm expecting some similar scenarios after the passage of a typhoon over Mindoro Island. And especially, as you can see here, these tropical cyclones trigger sediment suspensions that is highlighting all the shelf around the island. And if this mixture of water and sediments is advected towards the shelf break with enough momentum, this can lead to the triggering of turbidity currents in the continental slope. But what are the exactly triggering mechanisms? So what is the mechanism that can link tropical cyclones with marine turbidity currents? In this talk, I will try to demonstrate to you that coastal circulation can do the job. So the outline of this presentation are, in the first part, I will talk about cyclone-induced turbidity currents, so what we know about these mechanisms, these physical mechanisms, what we know about storm-induced coastal circulation patterns. I will present you in detail two case studies offshore the Philippines, and then in the last part of the presentation, I will give you some brand new results, and I will conclude with some remarks. So, if you have evidence that in a submarine canyon, offshore, and a high-extending island, after the passage of the tropical cyclones, a turbidity current occurred, your first guess would be that heavy rainfall caused by the tropical cyclones generate high river discharges in small and steep mountainous river deltas, leading to hyperpigmental flow from the river mouth that transit into turbidity currents along the canyon. And you would do that thinking to the Gaoping Canyon, which is a well-known example of this kind. Professor James View gave a talk in this webinar series where he disclosed most of the interesting details of this system. And I borrow these slides from him because he was, especially in the paper of 2012, he collected a very interesting and completed time series of precipitations and river discharges at the river mouth, and then of meta-ocean forcing, and also backscatters of sediment suspensions and measurements of temperature in the water column in the proximal part of the Gaoping Canyon. So he was able, with this time series, to link, especially to link the precipitation in the Gaoping River to the triggering of turbidity currents in the Gaoping Canyon, marked with a temperature anomaly on the bottom of the canyon. And he was able to do that for Typhoon Kalmaegi and Fong-Wang, which made landfall directly on the islands. But however, there was a fourth typhoons called Nuri that passed far away from didn't make landfall over the island, so it didn't induce strong precipitation and river discharges, but it induced very high waves, larger than 6 meters. And to these very high waves, it was possible to associate another temperature anomaly, so probably most likely a turbidity currents. So in the following, I will try to demonstrate you that cyclone-induced hyperpigmental turbidity currents are not always the case. Of course, I'm not the first one to, saying so. There are two papers, Pope et al. In 2016 and Gave et al. In 2017, that were able to link the timing of submarine cable breaks. Here you can see an example in the Gaoping Canyon, so how many cable breaks are crossing this canyon. So they were able to link the timing of cable breaks with the timing of passages of typhoons in the nearby area. And doing so, they identified 3 different mechanisms for the triggering of turbidity currents by tropical cyclones. The first one, type 1, a direct triggering that is synchronous with the passage of the cyclone and is associated with the meta-ocean forcing, so wave and wind-induced condition on the shelf, as you can see here. So associated with the steering of the sediment on the shelf by waves, and on the motion, the advection of this sediment by induced currents. And then they identified a second indirect triggering mechanism associated with peak river discharges, and in particular with the formation of hyperpigmental flows from river deltas. And then they were able also to identify a third type of mechanism of triggering of tropical cyclones that was indirect and delayed with respect to the passing of typhoons. And they associated this triggering to the reworking of sediment that was of large and rapid deposition of sediment associated with the tropical cyclones. I will talk about the first mechanism in the following, and to do so, I would like to introduce the main physical mechanisms that control the nearshore dynamics during a storm induced, for example, by a tropical cyclone. So if we have wind forcing an area close to the shore, we will have this transfer of energy from wind to waves. So we will have the generation of rough waves that proceeding towards the shore will increase in height due to the shoaling phenomenon. So when they will follow when they will feel the bottom, they will increase in height until they will reach an instability, and they will break in the surf zone. So the nearshore area, in particular the surf zone, is controlled by these mechanisms, by this energy that waves bring towards the shore, and then they transfer to the water column. So if we are in the simplest conditions, so waves proceeding over a planar beach in an orthogonal direction, this energy given to the water column will transform in an increase in mean sea level very close to the coast. And this is called wave and wind setup. And this will correspond to a motion of water and sediments in the offshore direction near the bed that eventually will result in the formation of sediment bars along the shore. If we complicate the system, so if we account for a wave that is coming with a certain angle with respect to the shore, we will also have the formation of longshore currents that will propagate and force the system parallel to this bar. Further complicating the system, so if we account for a three-dimensional evolution of the bathymetry, and especially if we, for instance, consider a sediment bar that is carved by some erosional feature, this erosional channel will affect the breaking and propagation and breaking of waves, leading to the formation of rip currents, which are jet-like flows induced by this three-dimensional configuration, and that are offshore directed and can eventually overpass the surf zone and the breakers. If we account for very energetic conditions, so associated, for example, with the occurrence of major storms, these rip currents can be very large. So here you can see an example along a constant beach that was approximately 300 meter large, and that goes offshore the breakers carrying sediments. Usually, these are called mega rips, and they are usually observed when the waves and winds forcing is interacting with a more complex bathymetry. So in this case, you can see a coastal embayments and the interaction with these waves propagating onshore with the curvature of these embayments can lead to the formation of a rip current, a very large and intense rip current in the middle of the embayment. There are many studies of mega rip circulation in embayments. Usually they identify as most likely location for the generation of these rip currents in the center of the embayment, and also at the sides of the embayment where some headland features can lead to the deflection of a longshore current in the form of rip currents directed offshore. And these currents are also very much important in terms of sediment transport. In this case, McCarroll in Italy in 2016 was measuring the bathymetry prior and after a major storm, and he was finding a strong localized erosion just in the middle of the embayment and in correspondence to the southern edge of the bay, probably linked with mega rips. We can study these systems by numerical modeling, And this is another case. This is McCarroll Italy in 2016. They were modeling the circulation, the storm-induced circulation in Perranport Beach in England, and they basically identify a mega rip current circulation and a longshore current circulation, and they were able to associate these coastal circulation to the sediment bypass, so the sediment transport and the bypass of this sediment from one bay to the other. Now, I will, now that I finished this introduction, I will describe the two study cases I will present you in the following. So we came back in the Philippines, and as you can see, we will investigated carefully what happened in Mindoro Island, offshore Mindoro Island, which is an island prone to tropical cyclones, to typhoons forcing. And in particular, in Tayabas Bay, offshore the Mindoro Island, a pipeline, a submarine pipeline, was displaced in two different locations. And this displacement of the pipelines were linked to the occurrence of turbidity currents. But what is extremely interesting in these two cases is that after the study of all the typhoons that pass nearby the area of interest during the lifespan of this pipeline, we were able to identify three different major tropical cyclones, but not all of them, even though they show similar tracks with respect, especially to the triggering area, not all of them were able to lead to pipeline displacement. So in particular, Nok 10 and Durian typhoon leads to the pipeline displacement, to the submarine incident in the Malalai and Baco submarine system, which is here, while Mellor typhoon was the most likely culprit for the submarine incident in the Magasawa and Tobig submarine system. So talking about the Malalai and Baco system that you can see here. So this is the Malalai and Baco River that are debouching in a very narrow shelf. And just offshore the shelf break, there is a very complicated system of submarine canyons carving the continental slope. So in this slide, I would like to show you how it was possible to spot turbidity currents. So why these pipeline displacements were linked to turbidity currents occurrence. And this was because from the analysis of the submarine system, it was clear that all the signatures of turbidity currents were present, in particular submarine canyons, but especially bed forms just characterizing the seafloor inside these canyons that were migrating upstream. You can see here a sub-bottom profiler section. The detail are in this figure here. And different bathymetric survey were highlighting a strong migration of bed forms in upstream direction. And if you consider all the talweg of these Malalai Canyon, you can see from mapping differences that probably associated with turbidity currents, there was a deposition and erosion of the sediment. In particular, there was in some location very strong erosions equal to 10 meters of the seafloor. Another signature of the passage of turbidity current was the sediment sorting in this submarine canyon system. So many sediment cores, piston and push cores were collected throughout the submarine system. And if you see on this, on the right side, the mud percentage that was found in this course, you will see how the canyon is coarser, so indicating the presence a seabed composition more coarse than in the interfluves in between two different canyons. And this is a clear indication of turbidity currents carrying coarser sediment all along the canyons. So, in order to identify the most important cyclones, the most critical typhoons that pass in the nearby of the study area, a tropical cyclone reanalysis hindcast was carried out for Verde Island Passage, which is here very close to the area of interest, and Tayabas Bay. And this hindcast, thanks to this hindcast, it was possible to identify as the three critical typhoons Durian in 2006, Malheur in 2015, and Nocten in 2016. And these typhoons were associated with the most severe metocean forcing. Here you can see the significant wave height in function of the distance of the eye of the typhoon, so the tracks of the typhoon with respect to the area of interest. And as you can see, the three most significant cyclones were in a radius of 50 kilometers from the trigger area. And all the other typhoons that you see are not important for this study case. I will not talk about that in the next slide because they happened not during the lifespan of the pipeline. So in order to assess the possibility of hyperpigmental flows from the Malalai and Baco rivers, a rainfall runoff model was carried out. And here you can see the input of this model in terms of precipitation intensity. You can see how the precipitation intensity is higher for Durian and Nocten, which are the triggering typhoons for this study case, while this precipitation is very much lower in the case of Malheur, and in the case of all the other perturbation, including monsoon. But after the results of this rainfall runoff model show that monsoons in particular are creating the most severe, the most high river discharges, higher than in the case of Durian, prior and after its occurrence, and higher than also Nocten. So already from this time series, we were convinced that hyperpigmental flows was not the most likely triggering mechanism for this study case, but we investigated the most likely sediment transport from the Malalai and Baco rivers, in particular the Malalai rivers, and we assume in a very conservative way some sediment grain size of 20 micron coming from the river. And even with such a conservative assumption, the sediment concentration, the runoff sediment concentration was not higher than some kilogram cubic meters. And so we studied with details the metaocean forcing induced, in this case, I will show you that one induced particular by Durian in 2006. So in this first graph, you see rainfall intensity and river discharge. And as you can see, the time series show how Durian did not generate a signal very much significant with respect to the prior typhoons and also prior monsoon that occur over Mindoro Island. But the very significance of Durian in this submarine system was the forcing, the metaocean forcing. So associated with Durian, we found wave height larger than 6 meters. And also associated with these waves, there were longshore currents larger than, very much larger than 1 meter seconds. So we did the same analysis for Mellor, and we compare the results of Mellor and Durian. So after Durian, there was the pipeline displacement was measured, while after Mellor, no pipeline displacement was found. And both the cyclones were actually inducing very high waves on the shore. But the big difference between these two typhoons, due to their different approaching latitude with the area of interest, was the currents, the littoral currents. And specifically, Durian was creating very strong eastward currents that you can see here. This is the Meta-ocean node from which these time series are extracted. So the red arrow is indicating the eastward currents induced by Durian, while Mellor, because it was passing in the south part, south of the trigger area, induced a current reversal. So the current, the large current, lower than 1 meter second, but larger than 0.5, so stronger longshore currents, was in the westward direction. And so it was hypothesized that this littoral drift was associated with also the steering of sediments due to high waves, was the most likely triggering mechanism for this study case. And to validate these hypotheses, a state-of-the-art numerical model of turbidity currents was run and was forced with these eastward littoral drift, and the results show how turbidity currents are triggered by these onshore conditions in the canyon, specifically in the Malai Canyon, and how they propagate downstream the continental slope, impacting the pipeline almost perpendicularly, exactly where the pipeline displacement was measured. And also proceeding further downstream, where the main canyon is becoming narrow, we have an increasing flow velocity, exactly where the second pipeline displacement was found. So similar results were carried out for Typhoon Nocten, which had pretty much the same forcing conditions. And the results were, in the case of after Typhoon Nocten, the erosion of a berm over the pipeline was observed. And so the results of the numerical modeling in terms of shear stress were compared with the erosion of the berm. And as you can see, these agree very well. So I would like to close this part of the presentation showing you a video courtesy of Octavio Sequeiros, where you can see the Typhoon Nocten approaching Philippines, losing energy when passing over the islands of the archipelago eastward of Mindoro. And when arriving close to Mindoro, close to the area of interest, creating very strong metocean condition, currents in the eastward direction, and then triggering sediment gravity flows that has exactly the same characteristic as those I described in the previous slides. So, this is the second system, and this is the second study case I would like to present you. So, we are offshore the Magasawa and Two Big River Delta here, and a pipeline displacement was observed in this location where the pipeline crossed the longest submarine canyon in this area, And this was observed in 2016 after the passage of Mellor and not Durian and Nocten. And in this system, we can see the same signatures in the previous submarine system. So the presence of gullies eroded offshore the river delta. And these longest features, this long submarine canyon, and a widespread presence of bed forms in all of the system. The difference with respect to the previous system is that the longest feature, so the longest submarine canyons, it is not directly linked to the river delta, but it is in correspondence of the middle of an embayment that is created by the delta lobes of the Magasawan tubig and a neighboring river delta that here you cannot see, but it's not far away. And another particular features of this system that I would like to highlight is the presence of these bed forms. So here you can see these yellow lines where sub-bottom profiles were extracted. Exactly these sub-bottom profiles that were showing bed forms upstream migrating, exactly like in the previous submarine system. But in this case, these bed forms were not inside the canyon, but were outside the canyon. And Heldemir Montes described similar features in a talk, I'm not wrong, 2 weeks ago. But the bed forms she described had the crest in the direction opposite to the canyon. Here instead, and they were linked with the overspilling of turbidity currents. But here we can see bed forms with crests, which are usually orthogonal to the direction of the turbidity currents, that are converging into the canyon just upstream where the pipeline displacement was found. So this is Typhoon Mellor passing south of the area of interest, and these are the time series extracted at a metaocean node and at the mouth of the river. So you can see that Mellor was able to induce large precipitation that corresponds to a delayed high river discharge, and also strong wind speed associated with high waves larger than 7 meters. And I will come back to this wind and wave rotation and also these sustained northwesterly winds. So this is the time series and the direction of, in particular, of the wind forcing. You can see the rotation associated with Mellor, which is clockwise, and the sustained northwesterly winds during the tail of the typhoon storm. So to assess the likelihood of hyperpigmental flows from the Magasawan to Big River, the same rainfall runoff model was applied, and in this case, the river discharge associated with Mellor was larger than the two no-triggering typhoons, so Dorian and Nocten, and it was also larger, even though comparable with the larger monsoon, in particular the one of 2008. And so we ran exactly the same analysis. On the basis of these river discharges, we try to evaluate the sediment concentration coming from the river. And one more time, assuming very conservatively 20 micron sediment grain size, uniform sediment grain size, we found sediment concentration of the order of some kilogram per cubic meter. And so initially this triggering mechanism was not considered as the most likely. So what we made, we studied the metaocean forcing induced by the three most relevant typhoons of interest. Here you can see a comparison with the one induced by Typhoon Durian that did not lead to any pipeline displacement, and Typhoon Malheur, which lead to the pipeline displacement. And you can see that due to the different approaching latitude, so Durian passing north of the trigger area, while Malheur passing south, they were inducing completely different wind and wave rotation. In particular, you can see here how the peak of the waves induced by Durian were coming from the northwest, and then there was a counterclockwise rotation. So winds blowing over the island and not inducing strong high waves and large nearshore currents. Exactly the opposite happened during Malheur typhoon. So to clockwise rotation of incoming winds and waves, and in particular, a peak of the typhoon storms with waves almost perpendicular to the coast. This was probably leading to the pipeline displacement. But how? So we ran a model of the coastal circulation induced by these three different typhoons. And what we found is that associated with the counterclockwise rotation induced by Durian, a longshore current all along the embayment was created, but no intense direction and sediment transport were predicted in the direction where the longest feature, the longest submarine canyons crossed the pipeline where it was displaced. And a particular mega rip circulation was instead predicted for the Malheur-induced coastal circulation. So this clockwise rotation of Malheur create an antecedent, a longshore current similar to the one of Durian, but then after the clockwise rotation, an opposite longshore current was created, and from the convergence of these two longshore currents, a mega rip developed right in the direction of the longest feature, of the longest submarine canyons that crossed the pipeline where it was displaced. So we hypothesized this mechanism, this triggering mechanism in the case of Malheur. And so waxing waves and winds coming from one side of the coastal embayments, and then associated with this clockwise rotation, the triggering of another opposite longshore current, forcing the system and converging with the opposite longshore current to trigger a mega rip circulation and a turbidity currents all along the longest southeasternmost canyon. To prove this hypothesis, what we made was extracting these currents and sediment concentration at the 10-meter bathymetric contour during all the stages of the Malheur storm. And what we made was to provide these forcing condition to a state-of-the-art modeling of turbidity currents, the ones used by our collaborator in Shell. And the results show how this mega rip circulation was able to trigger a very strong turbidity currents in the system, and how these turbidity currents develop along the longest canyon. These turbidity currents converge just upstream the location, the pipeline crossing, and impact almost perpendicularly the pipeline with velocity larger than 4 meter-seconds. And then we did the same modeling efforts for the other two typhoons. so Durian and Nocten, after which no pipeline displacement was observed. And what we found is that associated with the clockwise rotation of Mellor and the mega-rip circulation induced by this forcing, turbidity currents was observed. And there were associated with the counterclockwise rotation of the other two typhoons of interest, and in particular associated with the development of an alongshore current. No triggering was observed in the area where the pipeline displacement was observed. Only during Durian, the alongshore current, especially on the left side of this graph, was entering in the domain and creating some turbidity currents in the gullies offshore the river deltas. But no triggering was observed for Nocten. So in the last part, this is the last part of the presentation, I will try to describe some brand new results. And these are mainly modeling results. So the last part of the project was dedicated to the development of an application of Delft3D. So by the way, the model I used for assessing the coastal circulation was Delft3D. You can find very great description of how the model works from the talk of Dano Rowling in this webinar series. And so the last part of the project was just trying to develop an application of this model to study directly the turbidity currents within only one modeling framework. And this was done because the coupling, during the coupling of different models, you have to assume, you have to make a very strong assumption that can lead to strong uncertainties. And so we developed this model, and as you can see, we were able to predict pretty much exactly the same dynamics that I described in the previous part of the presentation. So a sheet flows developing along the continental slope associated with the alongshore current forced by the first stages of the typhoon. But then after the clockwise rotation of incoming waves and winds, the triggering of this mega rip current, and then the triggering also of a strong turbidity current in the longest feature. And in particular, if we compare the result of the two modeling, we can see how the convergence of the intensity of turbidity currents in correspondence of the pipeline displacement are pretty much the same. We were able to predict the velocity larger than 4 meters seconds, which are in agreement, conform with the displacement of the pipeline. And also, what I would like to show is how the model is able to evaluating the sediment concentration, the high sediment concentration induced by this mega rip circulation. And the last slide of results is dedicated to the river outflow. So we made exactly the same model, but we were including also the forcing due to the river flood induced by Mellor. And these are the results in terms of near bottom horizontal velocity and near bottom sediment concentration. And if you compare with the results, the previous results associated with the mega rip circulation, you can see that the river outflow did not create any significant strong near bottom currents, at least in correspondence of the pipeline displacement. And also the sediment transport was pretty much lower and directed in the opposite direction. And this is due to the sustained northwesterly winds that were acting in northwest direction during all the tail of the typhoon storm during the peak river discharge. So to conclude, we can say that turbidity currents are triggering, can be triggered by coastal circulation patterns. And of course, three main factors determining the forcing of tropical cyclones and the direct trigger of turbidity currents can be identified. So proximity, strength, and importantly, their approaching latitude. And on this approaching latitude depends synchronicity of cyclone-induced waves and currents, and also the rotation of incoming winds and waves. So another point is that direct turbidity current off the center of coastal embayments can occur. And this can occur when cyclone-induced rotation are primarily coastal bound. Also, the study of the tail of the cyclone storm needs to be studied in detail, because it can affect the simultaneous peak flood runoff, and thus the indirect triggering of hyperpigmental turbidity currents. And also, I hope I show you that the turbidity current modeling match field evidence in the form of pipeline displacement and seafloor signature, and thus they are useful for assessing turbidity currents, geohazard, and sediment transport phenomena associated with their occurrence. Thank you.
Hello, Gaetano. That's a wonderful talk. Very, very nice. Show the typhoon, the tropical cyclone-induced turbidity current, particularly in the small island and near the river mouth. That's great. Let's see. Let's open to the audience. Any questions, please?
Thank you, Paul.
Go ahead to unmute yourself. Okay, let's waiting while we're waiting the audience. Gaetano, so you see the depths of the turbidity current, I see can reach to 200 meters maximum in your study area?
Sorry, what do you mean as the depth of turbidity current?
The maximum water depths that turbidity current can reach in your study area.
I would say that in this case, we are reaching this narrowing point, which is about, so I didn't realize that here I didn't put, I delayed the data of the depth, but it's under 2, 3, 4. So I would say even 500 meters water depth.
Oh, okay. Okay, that's interesting. It's kind of, that those tropical storm is provide and cause the intensified longshore and then trigger a strong cross shelf. And that might be a trigger for the formation of that canyon system in the locally.
Yes, I mean, the canyon was there. The canyon is there, is present, and it is not linked with the river delta. So in general, probably these gullies offshore the delta are triggered by turbidity currents directly from the small mountainous rivers. But in this case, this is not linked with the two deltas. And in particular, something I didn't show because I was afraid to waste time, is that there is this head wall all over the system that is covered by tens of meters of sediment. So it's an ancient head wall. Yeah. But these, in the presence, in the correspondence of the head of the canyon, leads to very high, very steep bottom. And so if you have some movement of water and sediment there, this steepness can probably trigger stronger turbidity flows.
Yes, because the steepness. Yeah, I mean, this is somehow we can see it kind of analog if you look at even the west coast of Israel, because the narrow shelf and the plume from Nile, some cause that turbidity current cross shelf.
Yes, I saw the seminar by Uri, and it was a great talk. I see that the only difference here is that he was linking these sediment transport with oceanic currents, so very larger scale currents. And here we were able to link the occurrence of turbidity currents with smaller scale circulation pattern.
Yeah, that's very interesting. Other thing, place to take a look is the South America, Western coast, Argentina coast, like the offshore of the Biobío River. And, Anna Beneste, she talked about that. Other very interesting. Very good. So let's see our audience. Anybody have a question? Well, I know, Gaetano, I know it's turbidity current a little bit different from Hyperpigmental, but I'm not sure. Do you have any observation show that kind of a Hyperpigmental event during the storm?
During the two typhoon storm, no. I mean, all the rainfall basically the data we had was the pipeline displacements and the occurrence of very strong typhoons that were associated with these pipeline displacements. And that's why it was used a rainfall runoff model to assess the likelihood of hyperpigmental flows, because we didn't have any useful data on that.
I see that here. Okay, Gaetano, are you able to see the chat? He said, from Zhong Wei. Don't share this one. Don't share this screen.
Yes.
Don't share this screen.
Sorry. I stopped to share.
Yeah, you can end up the share. Here's the question, he asked you, can you give a little bit description of the sediments? If they are carbonate rich, or are there any reef island around? Or what's the terrestrial material different from the carbonate debris?
I actually had no information on on the nature of the sediment, but the information we had was mainly on the sediment sides and also inside the submarine system, not very close to shore. That's why we made a lot of hypotheses on the grain sides, also coming from the river. River runoff.
Yeah. Okay, Gaetano, we have two more questions. One from James Best. Go ahead, James.
Thanks, Paul. Gaetano, thanks. That was just a tremendous talk. Just the incredible integration of field work and modelling. It's just fascinating. I do a couple of questions. The one I was going to ask you is, so in relation to generating hyperpigmental flows, do monsoons generate any hyperpigmental flows whatsoever, or is it just solely the typhoons?
So that's a really good question. That I would say that based on the survey on the pipeline, monsoon were not able to trigger any significant turbidity currents, at least any turbidity currents able to displace this pipeline. So probably they were potentially they were able to trigger some smaller flow, but we don't have any information on that.
Okay, I just sort of wondering in terms of duration and intensity, if that's the case, but presumably monsoon underflows may be longer than typhoon triggered underflows. Is there any sort of indication from the subsurface as to distinct event beds for the big events rather than the slower background sedimentation from the monsoon events?
So talking about the first case, the Malay-Lion-Baco system, where the longshore current was the investigated triggering mechanism, I cannot answer your question. But in the second system, there were very widespread bed forms that were indicating the activity of the submarine system all along the shore. So I guess a monsoon would probably leave some signatures more related with the outflow of the river, and not all the submarine system along the shore.
Yeah, okay.
I hope I...
Yeah, no, thanks. That's a great answer. Again, thank you. It's just a marvelous talk. Really enjoyed it. Thanks.
Thank you.
So, Carlos, do you have any question, or you just want to make some comments? Carlos.
Thanks, Paul. Can you hear me?
Yes.
Gaetano, fantastic presentation. Really nice. Thank you. Now, there was a question about the sediment type, and I just wanted to clarify that they are not carbonate grains. They are siliciclastic grains. That's what we found here. And I think the question by Jim is excellent. We wish we had longer piston cores along the slope and a broader to be able to try to investigate that question of whether there's kind of a small flow events associated with this, and whether they are hyperpigmental or not. But they're most likely there are small events, but if they are triggered by hyperpigmental or even by smaller storms on the shelf, that's still an open question. So I think that's what the study at Gaetano demonstrated very nicely, is that you need the coastal dynamics, you need the resuspension by the waves, and also you need a current directed offshore to generate these flows. And I think this is a very interesting, even in the case where he showed that the flow, small flow is generated offshore the river mouth, right, the Gaetano. The flow dies out, it's small, but you need the resuspension from the river, from the longshore current to trigger it anyway. It's not just the river. You need the wave steering. So I think this is very, very intriguing and very interesting, because we hear a lot about hyperpigmental flow, and we don't hear much about the coastal dynamics associated with the storm events.
That's very good.
So I think in this case it's pretty well demonstrated, whether it's widespread. But anyway, thanks.
Thank you, Carlos.
Yeah, that could be a very interesting potential area for pilot study, because it's not big and it's not that deep. And if we can have some tripod, then we can see, definitely get a little bit in-suit observation particularly during the storm. And here there's a last question. Yeah, go ahead.
Sorry, Paula, I would say that the most uncertainty comes from the sediment onshore. So yes, it would be very nice to get more data onshore.
Yeah.
Especially in terms of sediment.
Sure. Here's the last question from Kai Chi. It said, how about the difference of the longshore current velocity before, during, and after the typhoon period? The longshore current velocity, do you have some estimates? So
before, during, and after the typhoons period, yes, I mean, the GIF I present show basically all the different stages of the storm. So the longshore currents start being lower than some tens of centimeters seconds, and then when these very high, strong waves reach more than 7 meter seconds, it becomes larger than 1 meter seconds, and then fade away. I hope I answered the questions.
Yeah.
Yes.
Okay, that's very good. A very, very interesting area, and because Philippines receive every year maybe more than 5 typhoons. So it's a good place to catch up the typhoon impact influence.
Yes. Yes.
Okay, wonderful. I want one more thing. We have a special talk given by Joyce Whiskey on December 1st. And I will please keep tuned. You know, I will send a notice. The time a little bit different. Will be a noon time Eastern Coast. Will be 10 a.m. for the mountain time. So he will talk an overview, summarize of the human impact of the global river and the delta. That will be a special talk.
Okay, nice.
Yeah.
I'm used to follow all your seminars, Paul.
Yeah. Okay.
I will follow also that one.
Okay. Cool. Okay. Thank you. Gaetano. So it was a great talk, and thank you very much. And so we can stop here.